The UAE is a federation of 7 emirates. Geographically, land distribution is heavily skewed, with Abu Dhabi controlling the vast majority of inland territory. Zooming in, Dubai operates with severe spatial constraints, originally possessing only a short, linear stretch of coastline along the Persian Gulf. By the late 20th century, Dubai faced an economic mandate to pivot its revenue model away from finite resources and toward international tourism and luxury real estate. To execute this model, the emirate needed high-value, premium coastal frontage. Tourists and property investors demand direct access to the water. This created an unsolvable geographic bottleneck. The economic survival of the emirate required hundreds of miles of beachfront property that simply did not exist. The engineering response to this spatial constraint was to manufacture new sovereign territory directly in the waters of the Persian Gulf. This is marine land reclamation, using dredging ships to spray massive arcs of wet sand into the open ocean. This satellite image shows the result of that process: the Palm Jumeirah, a fully functional urban district extending outward from the mainland. Looking closely at its complex branching geometry, we are seeing the largest and most ambitious marine land reclamation project in human history. But depositing material into the ocean raises an immediate geotechnical question. How do engineers build permanent urban infrastructure on top of loose sand in an active marine environment? Left unchecked, an artificial sandbank faces 2 existential threats: continuous wave erosion eating away the perimeter, and structural subsidence, where the heavy buildings sink into the wet foundation. Keeping these structures above water requires strict material sequencing and uncompromising calculations regarding load-bearing capacity. This cross-section of the Persian Gulf seabed shows 2 advantages: exceptionally shallow water and a flat, stable bedrock. First, engineers drop massive volumes of heavy structural rock, creating a rigid breakwater perimeter. Then, deep ocean dredging vessels spray marine sand inside until the compacted mass breaches the surface. Creating a single landmass of this scale requires hundreds of millions of cubic meters of raw geological aggregates, transported entirely by sea. This photograph captures the unfinished state of reclaimed land following deposition. The white sand fronds sit exposed against the deep water, entirely devoid of infrastructure. While the raw mass of the island requires brute force dredging, its final shape is dictated entirely by high-level economic mathematics. If the goal is simply to create more land, engineers could dump sand into a solid rectangular block. This animation demonstrates the fractal pattern. A straight line representing a standard coast folds and branches into the palm, maximizing the total perimeter. Converting a solid mass into thin strips exponentially increases the linear coastline, directly multiplying premium beachfront real estate. For the end user, this geometry guarantees a specific luxury. Every single residential plot possesses direct private sea access. Looking at this high-angle view of the finalized layout, the unbroken lines of luxury villas sit directly on the artificial beachfronts. The palm tree shape is a highly optimized spatial algorithm, engineered to extract maximum financial yield from a limited footprint. Constructing urban centers on loose sediment introduces severe structural vulnerabilities, specifically the threat of catastrophic liquefaction triggered by earthquakes or tsunamis. This tectonic map highlights a critical advantage: the safe distance between Dubai and major active fault lines. Because the emirate lacks severe seismic activity, it neutralizes the tsunami threat that would instantly wash away unreinforced sand structures. The true threat to the island comes from within: the sheer downward weight of vertical urban development. To prevent sinking, planners implemented strict load-bearing zoning. This compares the mainland's dense bedrock against looser reclaimed sand. Heavy skyscrapers must remain anchored to the natural bedrock, which supports their immense downward force. The artificial sand fronds are strictly zoned for lightweight residential villas, preventing subsidence. These artificial islands survive because engineers matched the architectural mass of the buildings exactly to the geological carrying capacity of the land beneath them. Following the success of the Palm, developers escalated the complexity of their coastal manipulation. This aerial photograph illustrates the transition to an archipelago of isolated landmasses, known as the world. By removing land bridge access, this layout relies on open water gaps between individual landmasses to artificially inflate privacy and exclusivity. Arranging these islands into a recognizable map of the globe serves a distinct secondary function. The macrogeometry acts as a high-visibility architectural branding tool, designed to be identified from commercial flight paths to attract international investment. The world islands represent the commodification of geography, where isolation itself is engineered and sold as a premium feature. Through this process, Dubai transformed its geography from a short desert edge into a sprawling, hyper-developed maritime hub. This chart compares the length of the original pre-2000 coastline against the total engineered coastline today. The dredging projects increased Dubai's coastal frontage by several 100%. This massive expansion relies on three technical pillars: brute force aggregate deposition, a favorable seismological profile, and strict load-bearing zoning laws. By physically building into the ocean, this engineering campaign bypassed the existential geographic constraint that threatened the Emirates' economic transition. Dubai proved that a nation's coastline is not a fixed natural border, but a variable parameter that can be systematically engineered from the seafloor up.